it starts off with basically vocabulary surrounding circles. And you'll have seen a lot of these before, but it's worth just going over before we dive into it. You'll have seen center, radius, no worries. The other bits are a little less intuitive from previous years. If you cut a line across a circle, we call it a chord. That chord splits the circle into two portions. It'll be a minor segment and a major segment. Minor less than half a circle, major more than half a circle. If you drag a radius around for an angle, you create what looks like a pizza slice, but it's called a sector. And that portion of the circumference, is called an arc, so part of a circle. And perhaps unsurprisingly, we can have a minor arc and a major arc. So, could you turn over? We are going to look at calculating the arc length, so part of a circumference. And a really good place to start with this is recognizing we can do this for a full circle fairly easily. So imagine we're given degrees. If we want the arc length, and we call it L, what I'm going to start off with is explaining the formula. I'll start with a full circle. So full circle, we call it circumference, and it is equal to 2 pi r. Now, in past years, if you wanted a quarter of a circle, you might multiply by a quarter. Yeah? So you do 2 pi r is all the way around, times a quarter will give you a quarter. Or you could times it by 3/4 to get 3/4 of a circle. Or if you just wanted a half, you'd times it by a half to get half a circle. But this bit here gives you a bit of a circle, yeah? So the way we get the arc length formula is we take a full circle and then we multiply by the amount of circle that we want. So for degrees, the length formula looks like 2 pi r multiplied by theta on 360. Theta meaning how wide that angle is. If that angle was 90, we'd be multiplying by 90 on 360, which is the quarter. So if we wanted the arc length from there to there, it's the full circle times a quarter, but this time the fraction is expressed in degrees. Now clearly we tidy this a little bit, because the 2 and the 360 can sort of cancel out, leaving us with pi r theta on 180. So if I gave you the values for the radius and the angle, you could tell me how long that arc length is by putting them into the formula. So that's degrees land. Let's look at radians. Hey. Richie. In radians, the starting point's the same. We're going to start with the circumference of a circle and multiply by some sort of fraction. So for here, circumference is 2 pi r, but for our fraction, we're not going to use theta on 360. Instead, we're going to use theta on the equivalent of 360, which is 2 pi. What that means is if we're given an angle of pi, and being given an angle of pi sounds like a really odd thing to say because we're not used to measuring angles in radians yet, but an angle of pi is half a circle. So if we wanted to find the arc length for half a circle, we would put in pi to here, which turns that fraction into a half, which is kind of neat. Now, simplifying this is quite nice as well. We have a 2 pi there and a 2 pi there. So it means that the arc length formula for radians is just theta times the radius. So, do you want me to do an example? Alright, let's do an example with, how long should the radius be?
15.
Cool.
0.2.
And I'm going to choose
0.2.
a 30-degree angle.
Wow.
Alright. If we have a 15-meter circle and a 30-degree angle, we would like to find this length here, that length there. The way we do that is, like, okay, we've been given a degree, so we're not going to use that formula, we'll use that formula. The arc length will be 15 times 30 times pi on 180. 15 times 30, it's 450? Feels like 450. 450 pi on 180. You can simplify from there, but I'm not going to. 45 on 18. Take 9 out of both. Was it 5 on 2? 5 pi on 2. Ish. Alright, and that's the arc length, or you get it in decimal. If, and I will do the first example from the book if I can remember it, if you want the arc length for radians, and you've just been given a section here, and this is 7, and that is 1 radian, the arc length is just 1 times 7, because we use this formula, it's just 7. Which is pretty neat. So if you're given an angle and a radius, the arc length is the multiple of the two if you're using radians. Which is part of the reason we like using radians so much in maths, and you'll see it come up again and again, where life with radians is just easier than life with degrees. And that's why next year you'll only use radians. So it's a matter of, when you do the textbook questions, figuring out whether you have degrees or whether you have radians, and just picking which formula you want to use. Not too bad. Alright, let's consider area of a sector. If we want to work out area of a sector, the setup is pretty similar. You start with a full circle, and then you work out what it would be if you just had a bit of a circle. So here, we're no longer after the arc length. Instead, we want this area. If we're wanting part of an area, we will remind ourselves that area is really just pi r squared, and that gets us a full circle. And then we multiply by some fraction. And if the fraction is a half, great, we get half a circle. If the fraction is a quarter, we get a quarter of a circle. If we're working in degrees, we multiply by theta on 360. So therefore, the area of a sector for degrees is pi r squared theta on 360. Can't figure it like that. Radians, very similar setup. Area is pi r squared multiplied by a fraction. Instead of the fraction being theta on 360, it's now theta on 2 pi. The pi's cancel. It will be r squared theta on 2. So if you wanted to work out the area of this segment here, sector rather, it's in degrees, so you would do pi times 15 squared times 30 on 360. If you're working out the area of this one, you would do the radius squared times 1 in this case, divided by 2, and it will get you the area. So the next section, and I think is probably the nicest, easiest one of the lot, it's a matter of picking which formula you want to use, whether you're in degrees, radians, whether you're wanting the length or the area, and subbing in. It might be worth noting that if you found this length here, the minor arc, how would you find the major arc going around the other way?
And you just like subtract.
Good, you can subtract. So you could find the full circumference and then subtract that from it, and you'd get the other one around. Any other way of doing it?
You could just do the same thing, but this time, instead of the interior angle, it would be exterior.
Yeah, good. Use the same formula, but use 330 instead. And if we put 330 into there, you'll get exactly what Z said. So bear in mind that they might give you one, but actually you need to use the other in order to work out what you're after, depending on what they're asking. So you can flick between the minor and the major fairly comfortably. Alrighty, so on your sheet, you should hopefully have 4 formulas. area, and then what was on the board previously was length. And that will be enough to get you onto 5B. Don't do them all, do one from each, and then 7 and 9 are more fun. Alright, go for it. And this isn't the last work for the lesson, we're going to go on after.